ever look at something like an airplane wing and just wonder how it can be so light but also so incredibly strong? Well, a big part of the secret is components with walls thinner than a credit card. But here's the catch, the big paradox. The very thing that makes them an engineering marvel, that thinness, also makes them an absolute nightmare to actually manufacture. So let's get into it.
I mean, just look at this thing. It's a high-precision aerospace part, and every single surface on it is machined to a tolerance that's, well, it's thinner than a human hair. It's basically a sculpture, carved out of a single solid block of metal. And the level of perfection you need, it's just staggering. Because in aerospace, there's absolutely zero room for error. Okay, so that gets us to the big question, right? If these parts are so important for making planes lighter, cars faster, and everything more efficient, why are they so ridiculously hard to make? What is it about machining a thin piece of metal that makes it one of the toughest challenges in all of modern manufacturing?
Well, it all boils down to what we're calling the thin wall paradox. See, when it's all finished, this part is a rock-solid pillar of strength. But while you're making it, it behaves more like a flimsy piece of aluminum foil. Its greatest strength, being thin and light, becomes its biggest weakness on the factory floor.
And this isn't some niche problem for a handful of companies. These components are everywhere. In aerospace, they're literally the skeleton of the aircraft. In the auto industry, they're how you make cars more fuel efficient and cut down on emissions, all without sacrificing safety. It's all about that push to be lighter, stronger, and better.
To really get what's going on, let's meet our first villain of the story, deformation. It's a pretty simple physics problem, really, but one with totally disastrous results. Because, as you can imagine, when you're trying to cut a wall that's only a millimeter thick, it doesn't exactly want to stay still.
This diagram here just shows it perfectly. As that cutting tool is moving along, the force of the cut is literally pushing that thin wall away. It bends just a tiny, tiny bit, kind of like when you push on the side of a plastic ruler. And here is the absolute key. You tell the machine, hey, make a perfectly straight cut. But because that wall is bending away, the cutter doesn't actually remove enough metal. And then, as soon as the tool moves past, the wall springs right back. So what's the result? You get a part that's too thick on top and too thin on the bottom. It's a dimensional error, and that means the entire part is scrap.
Now, if deformation wasn't already bad enough, our second villain is, honestly, it's even worse. It's called chatter. And this isn't just a little bit of noise, okay? This is a violent, high-frequency vibration that can completely destroy the part, the cutting tool, and sometimes even the machine itself.
And hey, don't just take my word for it. The experts over at Kyocera SGS Precision Tools put it pretty bluntly. They said, chatter, it's the bane of every machinist's workflow. It's the one thing that everyone in this industry has a healthy fear of.
So, what even is it? Okay, think about pushing someone on a swing. If you time your push just right every single time, the swing goes higher and higher and higher. Chatter is the exact same idea. The cutter makes a tiny little wave on the surface. Then the next time it comes around, it hits that wave, which makes it vibrate a little more, which in turn creates an even bigger wave. It's a feedback loop from hell, and it's called regenerative chatter. It can spiral completely out of control in milliseconds.
And the consequences are just brutal. First, you get a terrible surface finish. You can literally see ugly waves in the metal. The vibrations are so violent they can chip or even shatter the cutting tool. The workpiece itself can be ruined beyond any hope of repair. And in the worst-case scenario, all that vibration can actually damage the super precise bearings of a multi-million-dollar machine. It's bad news all around.
So, how in the world do you fight these villains? Well, for a long time, the answer was basically a mix of trial and error, a little bit of guesswork, and just slowing everything way, way down. But today, we've got much, much better answers. Let's start with the intelligent solution, making the machine actually think for itself.
The big idea here is called adaptive control. So instead of just running a program with one set of speeds and feeds, the machine uses an array of sensors to feel what's happening during the cut, and it adjusts its own strategy on the fly. The key is, it doesn't just react to problems, it sees them coming and stops them before they even start.
And this is how it works. It's this beautiful, continuous loop. First, it senses what's going on with force sensors, accelerometers, even microphones. Second, it analyzes all that data, figuring out how the part is behaving as it gets thinner. Third, its algorithms predict when chatter or deflection is about to happen. And finally, step 4, it adapts, instantly changing the spindle speed or how fast it's cutting to keep everything perfectly stable. It's happening hundreds of times a second.
But it's not all about fancy computers and sensors.
Some of the coolest solutions are just brilliantly clever engineering. This next approach is all about fighting physics with, well, more physics.
And you can really break these down into two main groups. You've got your hardware tricks, which are all about the physical setup and the tools you use, and then you have software tricks, which is all about being smarter with your programming and telling the tool how to move.
Let's run through a few of these. My absolute favorite is simultaneous double-sided milling. You use two cutters on opposite sides of the wall at the exact same time. What happens? The cutting forces completely cancel each other out and the wall doesn't bend at all. So simple, so smart. Other tricks include things like optimizing the tool path to keep the pressure even, or using special cutting tools where the blades are unevenly spaced to break up those nasty harmonic vibrations.
Okay, so all these smart, ingenious solutions sound great, but do they actually work? The answer is a huge, resounding yes. And the results aren't just a little better, they are game-changing. They turn a job that was nearly impossible into something reliable and routine. Just look at this data on vibration. Using a conventional approach, you can see the vibration just skyrockets past the danger zone, and that's when you get chatter. But with adaptive control, the system is smart enough to keep the vibration way down in the green, nice and safe, for the entire cut.
And what does all that stability get you? Speed. You can cut way faster. This chart shows how much metal you're removing per minute. The old way is slow, it's erratic. But the adaptive system, it just hums along at a super high optimized rate. That means parts get made much faster.
And the improvement in accuracy is just as incredible. Some studies showed that these strategies can cut down on that dimensional error, that bending problem, by 75%. And that's not just the difference between a good part and a scrap part. That's what lets engineers even dream of designing the lighter, more complex parts that are going to define the next generation of technology.
And the amazing numbers just keep on coming. We're talking about a 71% reduction in how rough the surface is, so you get a beautiful finish every time. And maybe the most important number for any business, first pass yield. That's the percentage of good parts you make on the very first try. It jumps from a shaky 78% all the way up to an incredible 96%.
And believe it or not, this is really just the beginning. The next generation of manufacturing is going to take this to a whole new level. We're talking about digital twins, perfect virtual copies of the machine and the part that let you simulate everything first. We're talking about machine learning systems that actually get smarter with every single part they make, and even something called physics-informed AI, which doesn't just see patterns in data, it actually understands the physics behind them.
And all of this leads to a really exciting final thought. For decades, engineers have had to design things based on what was possible to make, but now we're starting to remove those limits. So the real question becomes, what are we going to build when our machines can finally and reliably perfect the impossible?